Okay, so thank you very much, everyone. I think by now you remember me. My name is Anouar Benali. I work at Argonne. I also work at the University of Chicago for some weird reason, but that's another story. So I'd like first to just acknowledge that Computer Time and the BES, our funding agency, and then I'm just going to move to the talk, which is basically CIPSI, a simple method to converge many-body wave functions. So this is not really going to be a full talk. This is more going to be a demo to show you how easy it is to do multi-determinant, to generate multi-determinant wave functions. And it's so simple that I'm going to take the risk to do a system in front of you without failing, which is kind of... So we all know that this, and we all know that choosing basically a wave function or choosing a method depends a lot on what you're trying to solve. Basically, depending on the nature of the property that you're trying to get, if it's cohesive energies, chemical bonds, or if it's something very accurate and small like magnetism, you need to change the level of theory that you do. The good part is that you can mix these levels of theory with QMC to generate your wave function whenever you want. And basically, one of the key things to do, since every method has its pros and cons, is always, as we have seen, to improve the quality of the wave function that you are using. That's always a win, that's always true. If you can get a good wave function, your QMC value is going to be good. If you have the real wave function, you will have an error bar of 0 because you will be exactly on the right wave function. So one way that you have seen to take trial wave functions is to use multi-Slater determinant Jastrows. And this is a copy-paste from Miguel's slide, basically, that tells you that, well, if you take a series or a combination of Slater determinants, well, you're going to have a lot of chances to get a better description of your wave function. So even if you take an infinite amount of determinants, like let's say we start from a ground state, and here this is just a small example where we have just these occupied orbitals and we have these virtuals. If you do a CAS, that means that you will need to select your active space. You will need to know exactly what you're doing to select only the determinants that are within your active space. You need to know the chemistry of your system to select the right active space and everything, which is great. But the problem is that I am not a chemist. I hate chemistry. I am really bad at chemistry, and I really tried to do this, and I spent, I think, 3 months trying to understand how to do a CAS, and I just ended up like taking dices, throwing them, and deciding how many active space I was going to put. I know nothing. So when I discovered this method, where basically what we have to do here in general is, from this system, we need to do all the possible excitations to generate a determinant. So this is the original one, the Hartree-Fock one, or the ground state. So let's imagine we're going to do all the single excitations. That means that we move this one here. Then the second determinant, we move this one here. Then we do the double excitations. Then we move from this one here, here. Again, you see the thing. And then you start increasing. You're just going to start increasing and increasing and increasing your active space, and basically this method is exponential. So you take all the ones that I just showed you, and then you start, again, exciting them to the second excitation, third excitation, fourth excitation. So you can imagine that if you want to have a description of your active space completely, well, you're going to end up with millions and millions and millions of determinants. But when you do this type of calculation, what is important to know is that even when you do it with the hydrogen atom, most of your energy, the hydrogen dimer, most of your energy comes from the ground state. So this is the most important determinant. And then probably the first excitation that you do is also important because electrons are going to be delocalized somehow on that determinant. But do you really need the infinite space? Probably not, because you're going to just start adding smaller and smaller and smaller and smaller values. So at some point, you will even end up with something like this, where you have all the lower orbitals completely depopulated, and you'll have this. Do you really think that this is going to contribute a lot to the energy? I mean, the probability of presence of this is there, but the contribution to the energy is going to be really ridiculous. So it would be great to just, if we could just select the most important ones, don't you think? Like if you can find a criteria just to select the ones that actually contribute to a certain level to the energy, that certain level we can put it as whatever error we're trying to do. If it adds 10 to the minus 5 because this is what we are trying to get into that small energy, then perfect, let's do this. Well, this idea was, so this is the oldest paper that I found from '73. And I think there was someone else who, these guys, they say that they took the idea from someone else who thought about it like years before that. And it's very funny. So this method here was discovered, at least published in '73, then forgotten by people, rediscovered magically like 10 years later, then forgotten again, then rediscovered, and again, until recently, where now people are starting to say, hey, wait a minute, I think we do have the computational abilities to be able to solve this. So basically what it comes to is that we have our wave function, trial wave function, that is our normal Slater-Jastrow wave function. So we're gonna just construct iteratively, and basically what it means is we're gonna take our first, our ground state energy, and we're gonna start doing the single and double excitation on it. And for each one of these determinants, we're gonna evaluate the energy with the second order perturbation theory. So any contribution of the energy from the second order perturbation theory to the total energy, that means that that determinant is gonna be kept. And here we go, we have our criteria to select. So with this criteria, we'll just do all the excitations at iteration 1. And so we're gonna do the single and double excitations at iteration 1. We're gonna take all these determinants, evaluate the energy that the contribution at the second order perturbation theory to the total energy. If this contribution is large enough, we keep that determinant and we add it to our construction. If it's not adding anything, we throw it away and we do it again. So now we have our original ground state plus all the new excitations, and we start exciting them single and double. That means that compared to the first iteration, we are getting also the triple and quadruple excitations on the one that were already excited. And we do this iteratively all the time until we reach either we can set a number of maximum of determinants that we want, 1 million, 10 million, what have you, whatever you want, or a threshold, once the energy starts changing at 10 to the minus 4, 10 to the minus 5, 10 to the minus 6. So at this point, I don't need to know about the active space. I don't need to know which are the frozen orbitals, which are not frozen, which matter. I really don't care. The only thing that I care about is how many millions of determinants I want, or what is the change in energy that I want, and that's it. Iteratively, the best ones are going to be selected. So I know that I will have more chances to grab all the physics that interests me at that level of accuracy, and I just let it go. And I don't have to be a chemist to do this. So this has been, so CIPSI, this method has been named CIPSI or given many names, but the method that I use is configuration interaction using perturbative selection done iteratively, a little bit, and as implemented in a code called Quantum Package. And nowadays there are many codes doing the same things. Norm Tubman, who's here, also developed his own code based on this theory or slightly differences in the way we select the determinants. But this has been developed in a French group in Toulouse by Michel Cafarel, Anthony Schemama. I did not have any picture of Emmanuel Guinet, so I think if you don't have your picture on the internet, you deserve a stereotype. And Thomas Plancourt, who's joining my group at Argonne. So one of the first examples that they did with this was on the oxygen atom. And why I'm showing this one? Because it's very easy to realize what happens when you add QMC to this type of wave functions. Because we can imagine that in this concept, we're reaching a full CI approximation. Why should we care about adding QMC? We're already having a great wave function. Well, very simple. So here, the solid lines are the full CI value for the basis set that we want. So this is at a double zeta, triple zeta, quadruple zeta, and this is the full non-relativistic energy. So this is the exact energy. Someone had enough time on his life to do a full non-relativistic exact energy for oxygen, which is not that complicated, but yet. And this is the exact value we have. So basically, if we do any type of method, we're always limited by the basis set that we are using. So if you do a calculation full CI, you will at best get extrapolation for that basis set. Now, if we start with a number of determinants, as you can see here, using CIPSI, well, actually, we reach that limit of full CI very quickly, less than 10,000 determinants, and we're already at the accuracy, which is fantastic, because usually for this type of methods, you need number of determinants is completely insane and giant, and I have a slide about that. But when you add QMC on top of it and a DMC on top of it, basically for the double zeta, you fall here. Triple zeta, you fall here. Quadruple zeta, you fall here. What this means is that when you add quantum Monte Carlo on top of a basis set, no matter what your basis set is, you're going to get rid of that limitation of the basis set, and you're going to go beyond, because you're going to be able, through the diffusion Monte Carlo, to describe better that space that is described by your basis set, rather than just being stuck within the conformation of your basis set. So basically, by adding DMC on top of this calculation, you remove a lot of the error introduced by your basis set. As you can see, even with one determinant on this case, we're already better than if you use the quadruple zeta type of basis set, which is fantastic. Another example, and this is the last before I show you how to use this code, is for the hydrogen water. And this was just published recently by, again, the Toulouse group. You need to be careful with the Toulouse group, with the Caffarel group, and not Julien Toulouse. So basically here they compared to a full CI calculation done by Almora and Diaz, where they used double zeta, triple zeta, quadruple, and syncuple. Anyways, and you see here the number of determinants they used. They used 10 to the power 10. And with the 5 zeta, they had to use 10 to the minus 19 determinants to get this value of the energy. Well, using CIPSI and adding QMC on top of it with Jastrows, well, they used only 1 million for the 5 zeta, and only 100,000. And basically, the energies, when you compare the two energies, are pretty close. I mean, this is, you save so much. And also, and this is the part that I love a lot, and by the way, here you can see also the effect of the basis set, that you are just like completely killing using the DMC compared to this type of methods. So basically, by adding DMC, you really remove a lot of the effects of the basis set. And then you can do an extrapolation at infinite. And this is, by the way, the value that they find extrapolated is the exact value compared to experimental, to the most accurate experimental value. So this is fantastic. And now I think I can show you a demonstration, and I finished it at 9:57 this morning when I arrived, so to have many points, but let me try to just switch screens here. So basically the code is called Quantum Package, and here I'm just connected to a visualization machine, Kool-Aid. It's a small machine that has, I think, 12 cores, and this is, yes, Paul?
Perhaps it's worth mentioning that Quantum Package is free and up on GitHub, which is one of the reasons why we're using it.
Yes, so I have just a small slide about what we do with it after this. So basically, the beauty of this code, so it's a free code, as Paul just mentioned. It's on GitHub. It's called Quantum Package. You can download it. It's easy to install as long as you have GCC 4.6, which seems slow, but apparently I had a lot of problems with that recently with other people. Most of the calculations that I run with this code, I run them on my laptop. I do not need anything more. So this is how powerful the implementation is. And I'm gonna show you what you need. So basically you need, maybe, I'll just increase the size. So basically you just need this file as an input file. And this file, as you can see, is a normal file. An XYZ file, everything that is very typical. So the only thing you need to do is you do QP for Quantum Package. Here I'm going to just create the input file. Easy FIO is for easy file input-output, but that's OK. I'm going to introduce the name of the file. Now I need, of course, a basis set. So the code is completely linked to the EMSL basis set. You don't need to go download the basis set or try to put it in some format or anything. It's all there. The only thing you need to do is -B for basis set, and you pick whatever basis set you want. I'm going to fail, and look what it tells me. Oh, no, it doesn't work. Please choose any of this large set of basis sets that are all on the EMSL. I'm going to choose the CCPVDZ, the double zeta, because it's fast enough. And now, because I want it to go a little bit fast, I'm just going to use pseudo potentials. oh, it's also interfaced with the BFD side of pseudopotential, so I don't have to do anything. I just have to do -p BFD. Well, that's great. So now, if I do this, I can see what is on my file. And this thing generates the typical type of input files that you know. You know, the like you see everywhere, where you see your coordinates, your basis sets, and everything. But you don't generate this. You never touch this. And actually, even if you modify something that is not accepted, like let's say here, I'm gonna delete this line and add something like this. It did not accept it. If I go back to atom 2, it's back. So even if you introduce an error in the input file, it does not accept it. So it's really black box, stupid chemist like me free. So that's fantastic. So here I'm just gonna modify a small detail that I can tell you about it later, but just for the purpose of this demonstration, I'm not gonna go into too many details. But basically this is, I'm telling it, please do not do the full perturbation theory at the end of the calculation, because I think someone else is speaking. And also the other thing is that by default, I can select the number, either I can select the threshold, so whatever accuracy I want to reach, or I can select the number of determinants that I want to reach. So I'm just gonna tell it, because 10,000 is really too fast, so I'm just gonna ask it to do 100,000 determinants, because otherwise you will not have the time to see the demo. So this is 100,000, great. So, okay, so now my input file is ready, everything is ready. I'm gonna run, to start I need, of course, the fundamentals, so the Hartree-Fock one. So we're gonna do qp run, and you just say SCF, and now it's running your SCF, it's run the SCF. So now you have your Hartree-Fock energy, you have your Hartree-Fock energy that is in here, and that's fantastic. So now you're good. Now that we have our fundamental, everything is done. The only thing that I need to know to do my full CI run is qp run, and I'm gonna do full CI. And here we go. Well, okay, so wait. Crap, sorry. Oh, I'm just gonna let it finish because it's. So basically, what it's doing here is that, for example, it started very quickly, but now I can just, like, while it's doing this, it did the first iteration with one determinant, then it added the number of determinants, and it did the whole calculation for them, and then again and again, iterations after iteration. And here we were at iteration where we had 46,391 determinants selected, and now it's doing again the calculation on it, evaluating the perturbation theory, and doing all this on it. And at this point, we have selected 175,000. What it means that actually it would have needed to reach the accuracy that I wanted it a little bit more. So it just, even if I told it, hey, stop at 100,000, well, it's still trying with 175,000 because this is the number of determinant it got from the previous run. So it's going to run them. And now it's just closing everything at 100,000. It's just keeping the 100,000 that are the most interesting. And I think this is the last round. And in my mind, it took 1 minute yesterday. So as you can see, this is pretty fun because you really don't have to do anything too fancy with it. So it took 1.46 minutes to do this carbon dimer at 1.35 angstrom distance in full CI. Well, with 100,000 determinants. That's, I think, for someone like me who doesn't know chemistry and doesn't want to know chemistry, I'm very happy. So now we have our energies, and we can even compare the energies between the two. So this is the energy of the Hartree-Fock. And this is the energy of the full CI. So you can see here that we are actually 0.3 Hartrees difference between the two. So we already have a first drop in the energy that is quite important between the two for the carbon. So we can see that actually you gain a lot compared to just Hartree-Fock, but that's normal. I mean, it's Hartree-Fock compared to multi-reference. Now, of course, the important thing is that we want to add Jastrows and we want to do QMC to go beyond the effect of the basis set that we have. So basically, we do QP run and save for QMC pack. And because these two codes, quantum package and QMC pack, are fully interfaced, I spent 3 months with the group trying to build everything together. So, well, we just pushed this. Oh, whoops, I did not target, sorry. I did not put it on the file. So we just do this, and basically, it's just going to write everything. So these are all the determinants and the excitations. It just writes them on a file that I call c2.dump. And now I just use convert for QMC, which is the tool that you used for quantum chemistry. I just add -qp. I give it the name. And just for the fun, I can add 3-body Jastrow or whatever I want. And here you go. Now you have 2 files. So this is my wave function, and this is the typical wave function that you know. With these are the orbitals, and here we go. We have all our 100,000 determinants, all selected, all put in terms of excitations. So if you see the first determinant here, you see we have 8 electrons in the system. We have 4 alpha, 4 beta. The second one, you see that we did 1 excitation. We moved this one here to somewhere here. And same for this one. So you can see all the important determinants that CIPSI found are added to the QMC. And the only thing that you need to do at this point is just to run the application, so, which I did. So, but I did not do, the reason I finished at 937 or 57 is that I did the whole dissociation curve. And basically, using 256 nodes for on Vesta, like you did yesterday, for 30 minutes, you can do the optimization of the Jastrows and all the coefficients. Because if you remember from Miguel's talk, it's very important when you do this to increase even, to improve the quality of your wave function, to also do the optimization of the Jastrow parameters at the same time as these coefficients of each determinant. So doing this for approximately half of the determinants and the Jastrows, it took me 30 minutes on Vesta with 256 nodes, which is fairly cheap. So in terms of hours, I did not do the math, but this is, sorry, 256 multiplied by 16. So that's about 2,000 hours, 2,048 core hours, which is fairly cheap for this type of calculations. So now back to this, and whoops, and of course it killed my dramatic effect. That sucks. Okay. So I'm not going to compare to experimental values because, again, as I said previously, the basis set QMC reduces a lot the effect of the basis set, but it does not remove it completely. So if you start with a basis set that is as simple as double zeta, you cannot expect it to correct all the effects of the basis set and to give you the equivalent. So most of the experimental values for C2, which is a very hard problem, they go to a very large basis set, and I didn't want to scare you by giving you the example of the difference of the two, and I finished at 957. So just as a reminder, these are the only comments that I did, and actually I even skipped a few ones, but these are the only things that you need to do a QMC, to do a quantum package run. So it's 1, 2, 3, 4, 5, 6 lines, and you're done. You don't need to know quantum chemistry to type 6 lines. And this is what I find for the carbon-2 dissociation energy. So basically, this one here is the Hartree-Fock. This one here is using just CIPSI by itself. And we see that if we had started with the DMC just with one determinant, we are actually improving already better than CIPSI. But this is to be expected because this is the limit. This is limited by the basis set that we're using, while the QMC, or at least DMC, is going to go beyond. So it's normal to get this. But we can see that the difference between using multi-determinants and not using determinants is already improving a lot the value here of our wave function, which says that, well, in this type of systems, and it's known for the people who do C2 dissociation energy, you need multi-determinants. So in summary, because I think I went beyond my allotted time, CIPSI as implemented in quantum package is a great method. It gives you really great wave function. CIPSI in general is a very good method. It's implemented in many codes nowadays. It's becoming more and more something that people use. But the way it's implemented in quantum package is quite fantastic because it's a black box. It's fully interfaced with QMC pack. It's a free code. You can just go to GitHub, do quantum package, and you get the code. You don't need nothing in the sense that you really, the wave function is, the input file is as simple as it can get. You need 5 lines of codes. So again, this is very fun, but again, this is, these methods are exponential. So it's great for small molecules, for benchmarking. We try to do benzene dimers, which are quite large, but do not expect to do I don't know, DNA with this. Before maybe in 2067, someone will find a way to do it, but we cannot, or uranium. We cannot do uranium with this. But basically, when you have a system, when you're trying to do dimers, when you're trying to do small, very small clusters, and you're trying to see, even if you will need a multi-reference to do your calculations, or you're not sure about something, you can use this type of methods to be sure that your system is not multi-reference, to benchmark smaller systems, smaller molecules. A lot of us do quantum chemistry for tiny molecules or smaller things that can fit. The largest, it's of course fully interfaced with QMC pack, so you can add the Jastros and everything to get rid of the basis set. And just as information, I added this. The largest system that I did was about 200 orbitals and about 100 electrons, but that was on a machine that had 900 gigabytes of memory. So keep in mind that that memory memory requirement is very large. So you'll need the largest your system is, the largest your memory requirements are going to be. So yeah, and these are other things that I played with. This is the G2 test set. So as an example, the G2 test set took 3 days on my laptop for the whole molecules. There are like 50. It's pretty fun. And this is titanium oxide dissociation energy. Well, where actually here in this case, we just see that 1 million determinant or one determinant in the case of this titanium oxide did not change much in the energy. So this was a good test to say, well, for this type of binary, you don't really gain much, or at least the gain that you have is below whatever accuracy we were looking for. So, any questions? Yes.
What's the highest symmetry group available?
I beg your pardon?
The highest symmetry, like most codes stop at D2H, for example, and if it's D infinity H, maybe you want higher symmetry.
There are no limitations in the symmetries. They implemented maybe no. Have you tried to break their symmetry?
You asking me?
Yeah. Have you tried to break?
But various orbital symmetries. That's the problem with breaking the symmetry. Various points with various basis sets.
Yeah,
but they said they're going to put it in at some point.
Okay, so they're going to put some more, but the code is very alive, and basically they don't have many users who are their first real users. So whenever something is missing, they add it more or less very quickly. Again, I'm not a chemist, so I cannot answer all the questions about chemistry. That's the beauty of it.
So I know if people are interested in using this, they should presumably talk to you at lunch or this afternoon.
Yes, so I already talked to a few people. If you are interested, please come and see me. Again, I can just point you, the only thing that I can really help you with, as you've seen, is just point you to where the code is and to tell you how to copy the input files, but there is a tutorial on internet. It's really very simple to use, so, but please feel free to come and talk to me.
All right, so we'll restart at 10:50, and let's thank Anouar again.